So from the course homepage in week 5, there's a screen time data, and that will take you to this right here. And then what we want to do here is we want to just copy the column of numbers, but not the whole column. So I just want to go to the bottom. The last one's in row 62. I want to copy those. If you're watching this on YouTube later, then there'll be a link to this spreadsheet in the description of the video. And then once you do that, then wander over to StatKey. And we're going to do a hypothesis test on that. And we're going to compare to what we found the national average to be. So get this started. So again, I want hypothesis test for mean, and that takes you to the page called randomization test for mean. And there's 2 things you got to do here to get this started. And there's going to be several homework problems and a written assignment at the end where you're going to do something just like this. You're going to edit out whatever data is there. Control A to select all, delete, Control V to paste the numbers in. We don't have an identifier, but we do have a header row. I have hours up there. So then click OK. Different than a hypothesis test where you start generating, you also have to tell StatKey, what are we comparing this data to? And that, notice they have a null hypothesis here, mu. I'll explain null hypothesis in a little bit, but we looked up and we found the mu for the population to be about 6.5. So I'm going to replace that with 6.5. And then what that'll do is it'll rescale the axis down here with 6.5 in the middle, because that's what we expect the average to be according to that research site we found. Okay, so again, 2 steps to get a hypothesis test started in StatKey. First, you got to either find the right data set, and sometimes on the homework I reference one of these, or copy and paste the data into that. And then you have to say, what are you comparing this to? And that's called a null hypothesis. And here the national average is about 6.5. So then we set that there. Once you put your data in and set the null hypothesis, then you can generate. So I get a similar shape to what I had before when I did the confidence interval. The difference here is the center. Instead of being centered on the sample statistic, it's centered on what the population parameter was. All right, so before I continue with the next steps, I just want to explain what we got here. And I need a screenshot of that. To page, please. There we go. Okay, so we are performing a randomization hypothesis test. And to do a randomization hypothesis test in StatKey, number 1, you have to have a data set to pop in there. And number 2, you have to have something to compare to. So some things I should point out here, I have a variable X bar, and that is the average screen time of the MCC math students. And it's in hours per day. And I'm comparing that to population parameter, which is again an average screen time for US adults, again in hours per day. So the statistic that we're comparing has to match the description of the population parameter. Okay, so these pretty closely match. I'm doing screen time in hours per day. with the adults and the BMCC students, it was geared toward estimating recreational screen time as opposed to work screen time. BMCC math students tend to be US adults. So I've got a similar parameter and statistic here. And I'm trying to figure out if they are significantly different or not. Okay. Now, based on our hypothesis test, we were thinking that BMCC students watch less, right? As opposed to just being different. Different means it could be higher, could be lower. Right? And sometimes we will go for it could be higher, could be lower. I don't know. In this case, we have a claim based on our confidence interval, and that claim is that BMCC students watch less than US adults. Time, hours per day than US adults on average. Should mention average because we're doing averages here. So that's my claim. We have a value for X bar. According to the sample, the value is about 5.6-ish, 5.6. And then for the population, the value we looked up was 6.5. So 5.6 is definitely less, for sure. But is it significantly less? Is it far enough away to say, oh, BMCC students seem a little different than the average adult? All right, so let's see, where does our sample, so notice the 6.5 is already in the middle. That's mu, the population. So that's important. Population value goes in the middle. And our sample is about 5.6, so that's going to be, there's 5.5, there's 6. So I'm going to guess 5.6 is about right here. Does that look like it's more than 2 standard deviations to the left? Pretty close, somewhere in there. A standard deviation in this case is that 0.389. Right, so we could jump over that way and see how far away it is. We can have StatKey do it for us rather than trying to count ourselves. So let's do it. So again, rewind for a second. First step we had to do here is get the screen time data, either from the home page here, week 5, copy it, go to StatKey randomization test for mean, edit the data in, adjust the null hypothesis. Now we're ready to do a test. So again, let's see, what test can I do? Well, the tests are up here. We can do a left tail test, a 2-tail test, or a right tail test. Since my claim was a less than claim, that means I'm going to do a less tail, less than is to the left. There we go. Let's say. So back here, I'm going to click left tail. And then is that number right there my sample mean? Nope. So I should plug the sample mean in. That's up here. That key doesn't do that automatically. So next step after I hit left tail is I click down there and I type sample mean, which is 5.67. Okay, or enter. And StatKey tells me that about 1.2% of other samples are smaller. That's reasonably small, meaning this is far enough away. All right, let me do a screenshot of this. Actually, I'm just going to draw a rough sketch of it. So I'm going to summarize this here. Let's get out of order. Fix that real quick. Okay, new page. So here's what we have again for the screen time hypothesis test. So I'm just going to smooth out that sampling distribution. In the middle goes whatever the population parameter is. That's mu equals 6.5 hours per day. And then we found that our X bar is way over here. That was the 5.637 hours per day. And then StatKey calculated that that tail there was 0.012. And every time I run it, it's going to be a little bit different. So you might have not had that same number. That would be 1.2%. And what that means is 1.2% of other similar samples will be less than what our average was if we expect the average to be 6.5. It's a complicated value. Okay. Bottom line is what I usually look for, the cutoff for what that should be is about 5%. Okay. This thing right there is called a p-value. So my p-value is about 1.2%. We compare the p-value to what's called the significance level. And related to the 95% rule, 95% is usual, then 5% is unusual. So the usual significance level is 5%, or as a decimal, 0.05. And that is called alpha. That's the Greek letter alpha there. And so our usual is 5%. Sometimes we might make it smaller. Like if this was a matter of life or death, I might make alpha a little smaller than 5%, like 1 or 2%. If it's just like casual curiosity, we might make it 10%, but 5% is the typical cutoff. Okay. And we'll get more used to what a p-value means later, a little complicated. But the bottom line is to find a p-value, you've got to have a sampling distribution, which is what this is. In this case, a sampling distribution is a distribution of sample means. And I think I did like 7,000 similar samples, each of size 61. Based on the sampling distribution is always going to be centered on what we think the population should be for that mean. Population average we read was 6.5, and then we compare that to the sample data. All right, so again, this is the population value, the population parameter, and this over here is my sample statistic. And like the confidence interval, these two are far enough apart to say, oh, they don't seem to have the same average. There seems to be a significant difference. Okay. So in this case, our p-value happened to be smaller than the significance level alpha. Right? 0.012. I misrepresented my p-value there. I don't know how I got a 0.5 on that. Just 0.12%. Oh, that was supposed to be a percent. That's what went wrong. Is less than 0.05. And that means the claim that was made was, the claim was that BMCC students do watch significantly less. That claim appears to be true. Okay. So when your p-value is less, that implies the claim seems to be true. I can't definitely say it's true because there's a chance I made a mistake. True. And again, I'm using seems to be as opposed to saying is true because I don't know for sure. There's a 5% chance I made a mistake here. Question?
Is the significance level always going to be 5%?
Unless we say, yeah, so if it's not stated, it's assumed to be 5%. A lot of problems will just state it that way, but there are some situations due to sensitivity, we might make it lower. Like if we were trying to determine if some medication could cause death as a side effect, we want a low significance level on that to make sure we're not making a mistake. If we were trying to accuse some company of a pattern of harassment or discrimination, we'd probably have a lower significance level. And what that does is the lower the significance level, the less likely you're going to make a mistake and accuse somebody of something or accuse something of happening that's not necessarily true. So what we typically say instead of the claim seems to be true is that the sample data supports the claim. And what we need to get used to here is one, the mechanics of using StatKey to run a hypothesis test, and then two, explaining what the results of the hypothesis test mean. So I'm going to go into some details about that next. And then we'll do a couple of other versions.